Our second lecture in our learning unit on organic chemistry molecules has to do with recognizing and drawing functional groups. So we're going to build on content from our first lecture, which was learning how to draw organic molecules. And now we're going to learn how to draw and recognize functional groups. So conceptually, functional groups contain heteroatoms, which are non-carbon and hydrogen atoms. Now, as we'll see, there are going to be a couple of things that we learn how to name that are technically not heteroatoms. They're going to be just carbon-based, but by and large, when we refer to functional groups, they're parts of molecules that are not carbon and hydrogen. And what's unique about this is they create atoms or groups of atoms that are going to have unique chemical and physical properties. So that's why it's important to recognize these, because molecules that have similar functional groups are likely to have similar chemical and physical properties. So you might remember, we've actually already learned two functional groups already. We learned functional groups that are amines, so have an NH2 group in them. And this is going to be something, and I'm going to highlight here, when we write an R group, this just refers to the rest of the molecule. So anything that contains an NH2 group on it is going to be an amine. And we also learned about the COOH group, which really looks like this. It's a carbon doubly bonded to an oxygen and then attached to an OH. We learned this as a carboxylic acid. And why we learned about these two is these represented weak bases and weak acids. And so we've already learned about those, but now we're going to see them in the context of the other functional groups that are important for this chapter. So again, skills that you're going to practice, activities that we'll work on in this section are learning how to recognize and name functional groups or drawing molecules that have specific functional groups. So a little bit of a laundry list of problems to help you practice that. And in addition, I'm going to encourage you to look at problems 70 and 71 and name the functional groups that are there. And then as a way to practice our skills from our first learning unit, try drawing skeletal structures of the molecules that are shown in problems 61 through 64. All right, so this is actually going to be a pretty short introduction, and then we'll practice some problems. So not as long of a video here as we had for learning how to draw. So again, I hopefully give you a little bit of a preview here that highlights that functional groups are really the central organizing principle of molecules in organic chemistry. And so we abbreviate functional groups FGs. And again, these are important because that distribution of electron density in a functional group is how that molecule is going to have specific reactivity. So when we think about reactivity, we can think about chemical reactivity, but we can also think about physical properties that are related to intermolecular forces. So everything that we learned at the beginning part of General Chemistry 2 here, thinking about solubility and physical properties, also can kind of translate here into thinking about reactivity. Now your book goes into quite a bit of detail about how to name molecules here. And again, I'm just going to highlight here that every molecule that has a name has sort of a prefix and a root part of it. And we're not going to really deal with that too much. What I want you to pay attention to with molecules is what we call the suffix or the ending point. And that's important because that generally identifies the main functional group that are in a molecule. So for example, things that end in OL are alcohols. And so you might think about isopropanol, which you find in rubbing alcohol, or ethanol that you find in alcoholic beverages. They end in OL because that tells us the important functional group that's in that molecule. So that's again something that we'll think about and kind of translate into concepts here. All right, so this table, this chart, this flow chart, if you will, is available on Blackboard for you. I would encourage you to have this. If you can't print it out, try to at least have it available electronically to look at as you work through some of these problems. This is what I call a decision tree, and it basically kind of walks you through asking some questions to help determine what functional group is present in your molecule. Now keep in mind, you might have more than one functional group present in your molecule. So you're always going to start with this decision tree by looking at this first kind of left-hand corner up here. When you're looking at this first left-hand corner, you're going to be asking, are there any kind of these structures in your molecule? If there aren't, then you continue down this path. If there are, you're going to kind of move this way. So again, keep in mind, you might need to run through using this chart multiple times because there might be multiple functional groups. So I'm going to have available for you guys on Blackboard a link to some flashcards, some digital flashcards that you can use to practice naming these functional groups. So what I'm going to do just really quickly here is try to run through kind of how this is categorized and how you can use this chart, and then we'll actually apply it to some specific examples here. So the first thing you're going to be looking for are these 6-membered rings that have these lines in them. Okay, so if you have some of those, and we'd answer yes to that question, then you're going to say, does it have an OH group attached? If it does, this is a phenol functional group. If it's not, we just say that there's an aromatic functional group in that molecule. One of the things that we'll see is a lot of drug molecules sort of have this as sort of a building block, as a central scaffold that we see there. Okay, so that kind of gets us through 2 of our functional groups there. So these numbers here just kind of remind us how many different kinds of functional groups are within a particular category. So we've got 2 kind of aromatic-based functional groups. If you don't have one of these, or if you're looking at naming an additional part that's in a molecule, now we're going to go down and we're going to ask about specific heteroatoms that might be there. So the next question is asking, do you have an oxygen atom? If you have an oxygen atom, then you're going to ask the question, is it part of a carbon that's double bonded to an oxygen? We call this a carbonyl group. Now this is really important to highlight. You'll notice that carbonyl isn't one of these red things here. A carbonyl is not an actual functional group. A carbonyl is a carbon doubly bonded to an oxygen that's actually part of one of a bunch of different functional groups. So if you have a carbon doubly bonded to an oxygen, you need to look next door, because telling us what's next door is going to identify what kind of a functional group it is. So again, if what's next door is a hydrogen atom, you have what we call an aldehyde. Now, I highlighted this on the first page, but I just wanted to point out here, when we have an R here, that just stands for the rest of the molecule. So again, we're not concerned with what the rest of the molecule is here. We're just saying if there's a carbonyl, we're going to look next door to tell us what functional group that is. Again, if it's a hydrogen atom, we call that an aldehyde. If it's more of a molecule, so again, these R's are typically carbon atoms. Okay, if there's more rest of the molecule, we'll call this a ketone. If it's a nitrogen atom, and notice this nitrogen can be bonded to 2 hydrogens, 1 hydrogen and 1 carbon, or 2 carbons, we would call this an amide. If it has an OH group, or again, if it's deprotonated, it would be an O- group, right? This is going to be an acid, so it can lose that proton. We call this a carboxylic acid. And if it's got an oxygen, but then more rest of the molecule, this would be an ester. So a lot of these are going to look similar to one another from sort of a name standpoint. So we have to make sure that we get these right. All right, so again, these are going to be if we have a carbonyl group. Well, what if you don't have a carbonyl group, but you still have an oxygen? Okay, that is either going to be what we call an ether, if it's an oxygen between 2 carbon atoms, or an alcohol, if it's a oxygen between a carbon and a hydrogen. So look at this. We've already gotten through more than half of our functional groups here just using this chart. All right, so again, now we're going to ask about a different heteroatom. What if you have nitrogen with only carbon and hydrogen? If you have nitrogen with only carbon and hydrogen bonded to it, that is an amine. And you'll notice here we can have a nitrogen that's bonded to a carbon, and a hydrogen, a nitrogen bonded to 3 carbons, a nitrogen bonded to 1 carbon and 2 hydrogens, or in this case, 4 carbon atoms. And we're actually going to see that that's going to give it a formal charge of +1. So again, these are going to be amines. Just kind of highlighting now some things that look similar, but they're different. Amines and amides. look very similar, but we have to make sure that the amide we recognize still has that amine part to it, but next door it's got that carbon doubly bonded to an oxygen. So these are different. Okay. Up here we've got ethers and esters. You'll notice that these are a little bit similar. This is an oxygen bonded to a carbon and another carbon. This is an oxygen bonded to a carbon and then a carbonyl. So ethers and esters look similar, but they're very different. All right, couple of ones that we have to think about that have sulfur in them, another different heteroatom. If we have sulfur between two carbons, we call this a thioether. Notice the difference. This was an ether. Anytime we have sulfur stuff, we see the prefix thio. Okay? So again, thioether versus ether. We had an alcohol. If we now have an SH group rather than an OH group, that's a thiol. And two sulfurs bonded to each other, we call that a disulfide. All right, so kind of highlight what's going on here. Answered no to that six-membered ring, no oxygen. If we say no to nitrogen, we're down here. If we say no to sulfur, kind of a fail-safe here. So you're saying you only have carbon and hydrogen atoms? If that's not the case, you probably answered a question incorrectly. So go back and start over. But if you only have carbon and hydrogen atoms, there's only 3 possibilities for what we might see in our molecule. If there's only single bonds, we call this molecule an alkane. If there's not only single bonds, but we have double bonds, that carbon-carbon double bond means we have an alkene. Triple bonds, we have an alkyne. So kind of an easy way to kind of help remember this guy is we've got an A, an E, and a Y. Those are how those appear alphabetically. A is first, so single bonds. E would be second, double bonds. Y is third, so that's going to be triple bonds. So just kind of a little way to help you remember that. So again, I'll put some flashcards online. Most of the problems that you are going to have where you have to recognize these, you're going to have, it might be a multiple choice question. So you'll be able to pick which one it is. But you also might see a question where I'm going to ask you to draw a molecule that contains a certain functional group. So in that case, you'll need to know what these look like. All right, just a little bit more on 2 of the functional groups that have like an extra layer that we need to sort of think about here. So again, alcohols. Remember, when we have an alcohol, that's going to have an OH group that's bonded to a carbon atom. Okay, so here we see all of our OH groups. Now, one of the things we need to think about for alcohols is we need to ask the question, they're always going to be connected to a carbon atom. So OH groups are connected to a carbon atom. And we need to ask the question, how many other carbon atoms are attached to that carbon? I'm going to say that again because this can get confusing. We need to look at the carbon atom that's directly bonded to the oxygen atom. And we need to ask the question, what is the number of carbon atoms bonded here? So again, we're looking at how many carbon atoms are bonded to that carbon atom. It can either be 1, 2, or 3. If there's 1 carbon atom, this would be what we call a primary alcohol. Okay, what we have here, okay, is going to be, here is going to be a primary alcohol. This carbon atom is connected to 1 other carbon atom. So this is going to be a primary alcohol. Okay. Secondary alcohols are going to have a carbon atom that's bonded to our OH group that's going to be bonded to 2 other carbon atoms. So we should point out that this guy is also primary here, but this guy is secondary. Let me go through and just kind of highlight with my same colors here. This is the carbon atom that's bonded directly to the OH group, and it's bonded to one other carbon atom. So that's a primary alcohol. Again, this is a primary alcohol as well because the carbon that's bonded to the OH group is only bonded to one other carbon atom. Let's take a look at this other guy. Here's the carbon atom. So we need to ask how many carbons is that bonded to? And it's bonded to 2. So that's a secondary alcohol. Tertiary alcohols. We actually don't have a structure drawn of a tertiary alcohol, but let me draw one for you. If we've got a carbon atom that's bonded to an OH group, and let's say we bonded it to 3 CH3 groups. In that case, the carbon atom that's bonded to the OH group is bonded to 3 other carbon atoms. That would be an example of a tertiary alcohol. So when we have alcohols, not only did you need to recognize that it's an alcohol functional group, but I need you to be able to identify whether it's primary, secondary, or tertiary. All right, we can do the same thing with amines, okay? So when we think about amines right now it's going to be a little bit different because now we're asking directly about how many carbon atoms are attached to the nitrogen, okay? So in this case, we still need to look at the nitrogen atom, and now we're asking how many carbons are attached to that nitrogen atom. If there's 1 carbon attached, again, that's going to be primary. 2 carbons attached, that's secondary. 3 carbons attached, that's tertiary. Okay, so it really is asking how many carbon atoms are attached to the heteroatom. So again, going back here on our previous slide, we can see we're looking at, in this case, the heteroatom is there. So we don't have any carbon atoms that would be attached to that heteroatom. So we have to look adjacent to that and ask, okay, for the carbon that's attached to the functional group, how many carbons are attached for that? In this case, we're looking at the heteroatom. We're looking at that nitrogen and how many carbons are attached to that. So they've got some examples here. Let's make sure we can see them. These are both primary amines here. Okay, so again, we've got, let me color code this here. Here's the nitrogen atoms that we have here, and we're asking how many carbons are they attached to? Just 1. Okay, just 1 carbon atom. Now, we look at this guy. Here's the nitrogen atom, and we ask how many carbons are you attached to? That's going to be 2. Secondary amine. Now let's look at this last guy. Here's our nitrogen that we're talking about. How many carbons is it attached to? 1, 2, 3. That's a tertiary amine. Okay, so with alcohols and with amines, you need to be able to not only recognize that it's an alcohol or an amine, but be able to indicate whether it's primary, secondary, or tertiary. Okay, all right, the last thing to just kind of introduce here before we do a little practicing is understanding how this principle of chemical reactivity, comes into play here. And it all has to do with being able to draw dipoles. So hopefully everybody's good. We talked about dipoles at the end of Gen Chem 1. We talked about it again when we talked about sort of solubility and polarity and things like that. So what we need to be able to do is draw dipoles on molecules. Remember, any bonds that are between atoms that are not carbon and carbon or carbon and hydrogen are going to have dipoles. So again, when we have heteroatoms, that means we have molecules with dipoles. We're always going to draw our arrow to the more electronegative atom. Okay, so again, carbon and oxygen bonds are always going to be drawn like this. Carbon-chlorine bond. In this case, the oxygen atom is more electronegative than the hydrogen. Okay, so when we think about, and here's 2 terms that I want you to understand. Again, there's a lot in this chapter, especially this second lecture here, that are just about names and describing things. Okay, when we think about something that we say is a nucleophile, okay, we're talking about atoms that are electron rich. So we're always going to be pointing to the arrowhead of our dipole. because that's an electron-rich atom. When we talk about electrophiles, that's referring to atoms in functional groups that are electron poor. So that's referring to this carbon atom, or this hydrogen atom. That's electron poor regions of our bonds. If you learn this early on, it will help so much in organic chemistry. Just like we know magnets with opposites attract, when we do chemistry, we have reactants that are reacted and do chemistry with one another because we have things that are electron rich, that have electrons to donate to participate in chemistry, and we have species that are electron poor, electrophiles, that are happy to take in electron density. So chemistry happens between electrophiles and nucleophiles. I should have circled those in the opposite direction. Chemistry happens between nucleophiles and electrophiles, things that are electron rich and electron poor. That's not unlike what we learned in our last learning unit on electrochemistry, right? We have things that are electron rich and are willing to sort of donate electron density, and then things that are electron poor. All right, so again, I've highlighted this with this guy a little bit here, but just to reiterate, the carbonyl group, and remember, that's not a functional group. The carbonyl group is part of 5 different functional groups that we learned about. It is very polar. Again, if we were to draw a dipole for this, we draw it like this. We could actually draw a resonance structure for this that even magnifies even more the fact that we've got negative charge on the oxygen, positive charge on that carbon. And that makes this a very reactive functional group in biological molecules. So not anything that we're going to get to in this course, but if you look at a lot of different biological molecules, they are going to have this functional group, whether it's sugars, whether it's fats, whether it's proteins, they all have a carbonyl group as part of a functional group that's in those molecules. So really important functional group for biological reactivity. All right, so let's go ahead and let's practice a few problems. Again, I encourage you as you work through these, try working through the solution first using that flow chart. Again, I'm not going to spend a lot of time using the flow chart right now. I want you to try using it and then pause the video, see if you can work through it in these problems. I'm just going to kind of reveal what these functional groups are. So go ahead, pause the video, see if you can use that flow chart to figure out the functional groups in these molecules. All right, here's a functional group, carboxylic acid. Here's a functional group, ester. Here's a functional group. This is an aromatic ring. If you just write aromatic, that's fine. Let's go to this next guy. We've got another one of these aromatic rings. We've got an alcohol, but we got to go through and identify what kind of an alcohol it is. So there's the carbon that we need to look at, and it's attached to 2 carbons. So that makes it a secondary alcohol. And we abbreviate that second with two with a little degree symbol. All right? This guy here, we have an amine. Do the same thing. Remember, with amines, we need to be looking directly at the number of carbons that are attached to that nitrogen. So again, we're going to have 1, 2. So this is a secondary amine. All right, last guy here. We can have functional groups that are within a ring. So this is going to be a ketone. You'll notice, even though this is a 6-membered ring, it's actually not the 6-membered ring that looks like this. One of the things that I'm going to highlight here, it wasn't implicit in things that we've talked about before. You can have an aromatic ring look like that, or it can look like this. These are the same thing, but they are not equal to what we see here. There's only one double bond there, so that's not an aromatic ring. But when we do have a carbon, two carbons that are doubly bonded, that's an alkene. And we didn't really talk about this, so I'm just going to kind of write this one down, but this is not one that's part of your sheet that you need to know. This is called an alkyl halide. So it's an halogen containing compound. So even if you just circled the chlorine and was like, that's a halogen, that's important in just recognizing, hey, that's a heteroatom. That's not a carbon or a hydrogen atom. All right, so again, this lecture was all about identifying functional groups. And again, those are going to be specific groups of bonded atoms, particularly rich in heteroatoms that are nitrogen or oxygen, but as we saw, we can also have sulfur. And again, they're going to react in very characteristic ways. So that's why it's important to recognize these functional groups. So again, you need to be able to know functional groups by name and structure. So this is kind of grouping them here, ones that contain only carbon and hydrogen, ones that contain only oxygen, ones that contain that carbonyl group, so that carbon double bonded to oxygen, and ones that contain nitrogen and sulfur. So in addition to be able to recognize, draw, name all of these, I also want you to be able to look at molecules and tell me if something is electron rich or electron poor. So again, that's just pulling in previous skills of looking at dipoles, recognizing that anything that is electron rich is going to be nucleophilic, anything that's electron poor is going to be electrophilic. All right, so again, look at this sheet as a great way to practice kind of learning your functional groups. Okay, ideally you want to get to the point where you could just look at a molecule, see anything that's a heteroatom, and be able to recognize that functional group. But until you're able to do that, this flow chart might be helpful in that process. All right, practice. I think I'm going to save this practice for us to actually do in class. I'm going to encourage you guys to maybe try to work on it. It's available on Blackboard. Try to work on it before class. You know, we can then use that time in class. I'll go through them fairly quickly for you to check your answers. But again, you might benefit from having some additional practice here. So I think there's about 4 pages that we have here where you guys can go ahead and practice. So again, that's available on Blackboard. I'm going to wait and we'll do this one in class, and then again, we'll see if we have some more time to then start tackling some of our homework problems.